Hey guys, my name is IBM and today I've shifted from AS and A levels and I've decided to solve February March 2024 paper 4.2. One student has been putting me on too much pressure to solve to try and explain most of the concepts in this paper because he doesn't understand much of the questions we asked in this question paper. So I decided to solve this paper and give some explanations just to help this student and the rest of the students who are sitting for IGCSE this coming May, June. So without wasting time, I would like to take you to the question paper. This is Feb March 2024. The paper is supposed to be 1 hour and 15 minutes. I'll try my level best to keep time because this is IGCSE. IGCSE is very easy. Now, one mistake which students always make is using G as 10 even when it is redefined as 9.8 meters per second. That is a bigger problem. This paper is supposed to be 80 marks, and without wasting time, I'll go straight to question number 1. The figure 1.1 is a speed time graph for the first 5 minutes of a bus journey. Okay, so describe the motion between t equals 0.9 to t equals 2.9 minutes. So 0.9, I think it is here, and 2.9 minutes is around here. You see that the speed is constant. It's a horizontal line, which means a constant speed. So that means the speed is not changing. So here is simply say constant speed. Then from t equals 2.5.9 up to t equals to 3.5, which is here, this is 3.5. You see that the speed is decreasing, but it is a straight line. So it is a constant. This is going to be a constant deceleration. The speed is decreasing, but it's a straight line. So we say constant deceleration. 2.9 to 3.5. So this is constant deceleration. It is a deceleration because the speed is decreasing. But because it's a straight line, it is a constant deceleration. Now, we can't say constant speed here because the gradient of a speed time graph is going to be the acceleration. And the gradient of a straight line is a constant. So, along between 2.9, between this point here, 2.9 and 3.5, it is a straight line, which means it has a constant gradient, so it's a constant acceleration. Then between t equals 3.5 to t equals 4.5, 3.5 to 4.5, which is here, the line is along a zero axis. That means the speed here is 0. And any object which is at 0 speed, then the object must be either at rest, or you could say it is stationary. An object cannot be moving when the speed is 0, so it is either at rest or it is stationary. Of course, here, where the speed is constant, the object is moving with 0 acceleration. It is not at rest, but the acceleration is 0. It is not speeding up or slowing down. So you should mark the difference between those two graphs, especially the last one and the first one. Then another bus travels at a speed of 8.9 meters per second. The brakes apply a constant force, and the bus speed stops in a distance of 23 meters. This bus has a mass of 18,000 kilograms. Calculate the kinetic energy of the bus before the brakes are applied. So we know that kinetic energy Ek is always given as a half mv squared. So this is going to be a half times the mass, which is 18,000, then times the speed, which was 8.9, and this is squared. So I'll just press my calculator. A half is the same as 0.5 times 18,000 times 8.9, but this is squared. So this gives me 712890. So this of course rounds off to 710000. So 1, 2, 3, 4. So I could write 7 71000 in joules, or I could divide this by 1000 so that it becomes 710 kilojoules. Note that the new setting now eliminates most of the units in paper 4, because we expect that students who do paper 4 are extremely smart students who should be able to know all the units, most of the units for most of these quantities. So most of the questions will not have units, so you should be able to write there the units. Then calculate the force applied to stop the bus. Since we have the distance it moves and the brakes apply constant force, so it means the constant force is applied to bring and the bus stops in a distance of 23 meters. So it means the work done is against the kinetic energy. So it means the work done here to stop the bus, the work done by conservation of energy, the work done should be equal to the loss in kinetic energy. So the work done, remember, is force times distance, and the loss in kinetic energy should be 71000. You could use 712,890 joules. N of these. So if I make F the subject, so F is going to be 71000 divided by the distance, which was 23. So the work done is equal to the loss in kinetic energy. So as it loses kinetic energy, work is done against this force, which is work is done by this force to make sure that it loses kinetic energy. So this is going to be that. So I want to use 71000 divided by 23. So this is giving me 3869, or approximately 31. So this is approximately 31,000 newtons, or it can be 31 kilonewtons. So here you can write one of those two, maybe 31,000 newtons or 31 kilonewtons. Define impulse. Of course, we know that force is equal to the rate of change of momentum. So when I multiply both sides, I have force times t is equal to the change in momentum, and this is the same as impulse. So I could say impulse is force, product of force times time, or impulse is the change in momentum. So impulse is going to be force times time, for which the force acts. Force times the time for which the force acts, that is impulse. The figure shows a rocket and its exhaust gases. The exhaust gases are emitted from the rocket with a velocity of 1,400 meters per second and at a rate of 2,800 kilograms per second. So this is mass over time. Okay. Show that the force exerted on the rocket by the exhaust gases is 3,900 kilonewtons. So state the equation used. We know that force is equal to the rate of change of momentum, and force is equal to change in momentum is mass times change in velocity, or it is the change in momentum is going to be change in m times v divided by t. So this could be m times change in v over t. So we already know m over t. All we need is the change in velocity to give us the force exerted. So the force is going to be m over t is given as 2,800, then times the velocity. The exhaust gases are emitted from the rocket with the velocity of that. So we can consider the change in velocity to be just 1,400. So this is going to be 1,400. And if I press my calculator, 2,800 times 1,400. So this is 3920. 3920,000 newtons. If I try to divide this by 1,000, it gives me 3920 kilonewtons, which is approximately the same as 3900 kilonewtons as required. Then calculate the maximum mass that this force can lift from the ground. Ignore air resistance. So if the resultant force, of course F is the resultant force upwards. So the resultant force is going to be equal to, at maximum force, at maximum, calculate the maximum mass that this force can lift from the ground. Ignore air resistance. So if we consider the maximum force, then there is, the maximum mass, it means it will give us the maximum weight. So the maximum weight must be balancing with the resultant force, or the force exerted on the rocket upwards. So the force upwards should be equal to the weight downwards for maximum mass. If the force upwards exceeds the weight, then the rocket accelerates upwards. So at maximum mass, the weight is equal to the force upwards. So at that point, I would simply say F minus the weight downwards should be equal to 0 at maximum mass or maximum weight. So the force F minus mg should be equal to 0. So the mass m is going to be equal to this force divided by g, which will be equal to 3, 9, let me use 0, 0, 0, 0, 0. Okay, but I would prefer to use that, but it's fine. Divided by g. They said you should use g as 9.8. So I would just divide this. So 3900000 divided by 9.8. So this is 3.99 times 10 to the power of 1, 2, 3, 4, 5 times 10 to the power of 5 kilograms. Or you can round off to 4.0 times 10 to the power of 5 kilograms. Then a car has a weight of 13,000 newtons. The car is supported by 4 tires. The weight is 13 newtons, supported by 4 tires. The area of each tire in contact with the road is 0.016. So that means the total area is going to be 4 times 0.016 meters, because there are 4 tires. Calculate the pressure on the road due to the weight of the car. Okay, so the pressure is equal to the force over the area in contact with the road. So the force is 13,000. The total area is going to be 4 times 0.016, which is going to give us 13,000 divided by 4 times 0.016. So this is 23,125. 23,125, or you can round off this to approximately 201,234. That is 200,000, or you can write this as 2.0 times 10 to the power of 5 pascals, or you can write this as 200,000 or 200 kilopascals. So this will be approximately 2.0 times 10 to the power of 5. I try to avoid writing one significant figure, that's why I may not write this. But I can write 2.0 times 10 to the power of 5, or you can write 2.03 times 10 to the power of 5 pascals. This is pascals. Explain in terms of particles why the air pressure in the tires increases when the car travels along the road. Of course, when the car travels along the road, the particles of the air in the tire are going to be moving faster. That's number one. As they move faster, they collide more frequently with each other and with the walls of the container. In fact, they collide even harder with the walls of the container. If they collide harder with the walls of the container, they exert a greater force onto the walls of the container, therefore a greater pressure. Okay, so simply say the particles of air, or the air particles in the tire, move faster. Move faster when they move faster, they collide more frequently and even harder. They collide more frequently and harder with the walls of the tire. So they collide more frequently and harder with the walls of the, because they are moving faster, with the walls of the tire. And if they do that, so the force they exert increases. So the force exerted on the tire wall increases. The force exerted on the tire wall increases, and hence, remember, pressure is force over area, and hence the pressure, in the tire increases. Okay, so that is why the air particles, why the air pressure in the tire increases. A gas cylinder contains helium gas at a pressure of 2 times 10 to the power of 6. A volume of 0.026 meters cubed of the compressed gas is released from the cylinder into balloons. Each balloon contains 0.015 meters cubed of helium at a pressure of 1.0 times 10 to the power of 5 pascals. The temperature remains constant. If the temperature remains constant, then it means P is inversely proportional to V, or PV is equal to a constant. Okay, calculate the maximum number of balloons that can be filled. So first of all, we need to find the volume, because each balloon has a volume, contains 0.015 meters cubed, and the volume of 0.026 meters cubed of the compressed gas is released from the cylinder into balloons. So we need to find out which volume is released into the balloon. So we know that P1 V1 is equal to P2 V2, or PV is equal to a constant. So V2 is going to be equal to P1 V1 divided by P2. P1 is 2 times 10 to the power of 6. Volume 1 is 0.026. P2 is 1.0 times 10 to the power of 5. So I'll just press my calculator to get the volume, which is released from the cylinder into the balloons. 2 exponent 6 times 0.026 divided by 1 exponent 5. So that is 0.52 meters cubed. So this is the volume which is released into the balloons. But each balloon takes a volume of 0.015 meters cubed. So the number of balloons is going to be 0.52 divided by 0.015. So I'll divide this by 0.015. So this is going to be 34.6. So 34.666 recurring. So it means the 35th balloon cannot be filled. So I'll just take 34. I can't round off to 35. So this is going to be 34. We cannot round off. It is not 35. You can't round off to 35 because it means the next balloon, there is no volume that can fill up the next balloon. So we just take 34, not 35. Not 35. So define specific heat capacity. Of course, specific means a unit mass of 1 kilogram. And heat capacity, of course, when we talk about heat capacity, we are raising the temperature of a substance by maybe 1 degree Celsius. So specific heat capacity is going to be the thermal energy or heat energy. Thermal energy needed to raise the temperature of a unit mass, or of 1 kilogram mass, temperature of a unit mass. When I say unit mass, I'm referring to 1 kilogram, a unit mass of a substance by 1 degree Celsius. That amount of heat which is required to raise the temperature of a unit mass of a substance by 1 degree Celsius is what we call specific heat capacity. A volume of 0.0024 meters cubed of oil is heated in a pan for 7 minutes. The temperature of the oil increases from 20 degrees Celsius to 180, which means the change in temperature is going to be 160 degrees Celsius. The density of the oil is 910 kilograms per meters cubed. The specific heat capacity of the oil is 2000 joules per kilogram. Calculate the mass of oil in the pan. So we know that mass is equal to density times the volume. The density has been given as 910 and the volume is 0.0024 meters cubed. So I'll just check with my calculator. 910 times 0.0024. So this is 2.184, which is approximately 2.2. So I'll write the mass as 2.2. Remember, this is mass, so it is in kilograms. I use the SI units. Then calculate the energy required. Calculate the energy required to increase the temperature of the oil. So we know that energy required is equal to mc times change in temperature. So the mass is 2.2. Specific capacity is temperature of the oil. Specific heat capacity is 2000. So this is 2000. Then the change in temperature is 160, or it is 180 minus 20. So this is 2.2 times 2000 times 160. So I'll just check my calculator. 2.2 times 2000 times 160. So that is 704,000. So I will write 704,000. 704,000. And this is energy, so it is in joules. Calculate the power required to supply the energy calculated. Of course, we know that power is the rate of transfer of energy, so it is energy over time. So this is going to be 704,000 divided by the time. The time was 7 minutes. So we change it to, because the energy is in joules, the time should be in seconds. So I'll say 7 times 60 to change it to seconds. So I have that divided by 7 times 60. So this is 1676. 1676.2 watts. Or I can round off to approximately 1700. So I'll write 1700 watts. Answers look so beautiful when you write them like that. So here is a blank page. Table shows applications of regions of electromagnetic spectrum. Complete the second column of the table with the region of the electromagnetic spectrum used for each application. Choose from the regions in this list. Okay. So Bluetooth data connection. Of course, we know that Bluetooth is either radio waves or microwaves. Any of those two, either radio waves or microwaves. So here the answer could be radio waves or microwaves. Any of those two. Radio waves can be used for Bluetooth or microwaves, depending on the wavelength. Then optic fibers. Of course, optic fibers is always infrared. optic fibers, that is normally infrared, that is transmitting signals using light. The light which is normally used is infrared. Security marking, I think security marking is normally ultraviolet. Security marking is normally ultraviolet. Sterilizing foods, this is normally gamma rays. Gamma rays. From that, it could be X-rays, but normally gamma rays. Then wireless internet is still microwaves. So wireless internet is normally microwaves. Sterilizing food, from the list we can choose gamma rays. Then because gamma rays can destroy bacteria. Security marking, that is normally ultraviolet. Optic fibers transmitting signals, that is normally infrared. Bluetooth data connection is normally radio waves, but can also be microwaves. Okay. Then state the approximate speed of radio waves. All waves travel at the speed of light, which is 3 times 10 to the power of 8. So this is 3 times 10 to the power of 8 meters per second. The figure shows successive crests of a wavelength of a wave after a plane wave has passed through a gap. So we notice that diffraction here is maximum. If diffraction is maximum, it means the wavelength of the waves is the same as, or approximately the same as, the size of the gap. Remember, for diffraction, the rule is very simple. The wavelength remains the same after diffraction. The wavelength remains the same. So I'll just try to measure the distance between these wavefronts, and I'll use the same distance to draw the same separation to draw the wavefronts. So from my rule, I'm seeing it is about approximately 1.1 centimeters approximately. Let me check the size of the gap. The size of the gap is also approximately 1.1 centimeters. So I'm going to draw wavefronts which are approximately 1.1 centimeters apart. For the diffraction to be maximum, the wavelength is the same as the size of the gap, and we see the bending here is maximum. So 1.1. So I'm going to separate these wavefronts by a distance of approximately 1.1 by eyesight. So okay, so these are going to be parallel wavefronts which are approximately a distance of 1 point. This distance here, you just aim at ensuring that this distance is the same as this distance here, because the wavelength is going to be the same. For the diffraction to be maximum as shown here, the wavelength is the same. So the question was, draw 3 successive crests before the wave reaches the gap. So these are my successive crests. They are parallel, and the separation, of course, you try to measure and ensure that this distance is the same. This is the wavelength, and it's the same as this distance here, because the wavelength remains the same when diffraction occurs, which is approximately the same as the size of the gap. Then on the figure 5.2 shows a much wider gap. A plane wave of the same wavelength. The wavelength has not changed. A plane wave of the same wavelength as in B Roman 1 is incident on the gap, as the gap from the left side of the barrier. So draw 3 successive crests of the wave after the wave has passed through the gap. So if I try to draw the previous wavefronts, the gap has increased. So let me first draw the previous wavefronts here. I'll just try to estimate approximately 1.1 centimeters. So the wavelength, the size of the gap has changed. So it means the diffraction decreases because the gap is now the wavelength is less than the size of the gap. So diffraction decreases. So the waves will be almost straight here at the center. But the wavelength is going to remain the same. So I have to estimate the wavelength to be approximately 1.1 centimeters. But then they will just slightly curve at the edges. So I'll curve these ones at the edges. Okay, so the diffraction would look like that. It's not as maximum as the one which we had seen previously, where the wavelength was the same as the size of the gap. Compare the first one, the diffraction is maximum, the bending is maximum because the wavelength was approximately the same as the size of the gap. But here, the size of the gap is much bigger than the wavelength, so the diffraction is smaller. So that's why we have a straight part in the middle of each of these waves. Then on the figure, draw three successive crests of the wave after the wave has passed through the gap. So I've already done that. The figure shows a full-scale diagram of an object and its image I produced by a converging lens. The lens and its position on the principal axis are not shown. Okay. On the figure 6.1, draw a single ray to locate the position of the center of the converging lens. So this is the image, the other is the object. So I want the position of the center. Remember, there is a ray which goes through the optical center, and this ray is not does not undergo deviation. So I'll just draw from the top of the object to the top of the image, and this ray undergoes no deviation. So this ray must be passing through the optical center. Okay, so that is the ray. So they said draw a single ray to locate the position of the center of the converging lens. So this is the ray. It does not undergo deviation. Okay, then so it means the position of the center of the lens should be here. A line to represent the position of the center and label the line L. So I'll draw a vertical line here. So I'll call this one L. Okay, those are 2 marks free. Determine the focal length of the lens by drawing another ray on the figure 6.1. So to find the focal length, I know that rays parallel to the principal axis they are deviated through the principal focus. So I'm going to draw a ray from the object parallel to the principal axis. I'm going to try as much as possible to make it parallel. Okay. A ray parallel to the principal axis converges through the principal focus. So these rays, of course, they meet at the point where the image is formed. So I must converge this ray up to where the image is formed. That's a very poor ray because it's not meeting at the tip. It's still very poor. At least that one. I can take that one. You can draw a better ray on your question paper. So that point is going to be the principal focus where it crosses the principal axis. Determine the focal length of the lens by drawing another ray on the figure 6.1. So I have to measure the distance. This is going to be the principal focus. I'll call this F. So I need to measure this distance here. Now, let me try to bring this back to its original position. I don't know, I don't remember the actual size of this, but it may, when I measure from here, I may not get exactly the same answer as you when you measure from the question paper. But let me try to measure from my, okay, when I measure from my computer, I'm getting 2.1. So you can also measure from yours, because this is, if you print the question paper, you are most likely going to get around 2.1. So this is 2.1 centimeters. So we are simply measuring this distance here, and it is approximately 2.1 centimeters. You may get 2.2 or you may get 2.0 centimeters depending on how you printed the question paper. But the correct answer is approximately 2.1 on the actual size of the question paper. The object is moved 2.0 centimeters closer to the lens. Closer to the lens. State two changes to the characteristic of the image. So if I move the focal point, the object is moved 2.0 centimeters closer. We are moving, remember the principal focus is 2.1. So if we bring the object 2.0 centimeters closer, it means u is less than the focal length. And when u is less than the focal length, the image cannot be formed behind what? The screen. The image is going to be formed in front. If you remember your principles of X-ray forming X-ray diagrams, if the object distance is less than the principal focus, the image cannot be formed behind the screen, behind the lens. It is formed on the same side as the lens. So that image which is formed on the same side as the object is considered to be virtual. That's number one. And that image which is formed in front is going to be it's actually going to be upright. It is going to be vertically upright. If the object distance is less than the focal length, the image is formed on the same side as the object, and the image is going to be upright. So the image is on the same side. It will be on the left hand side of the lens, and the image will be upright. Draw the circuit symbol of a potential divider. Of course, by now we should all know what a potential divider is. So we need a resistor or a resistance wire like that. And then we need to put something which adjusts the resistance. That is a potential divider. The figure shows a circuit. So this is a fixed resistor. This is a variable resistor. Calculate the V out when the value of R is 3 kilo ohms. So we are going to use the potential divider formula. VR is 3 kilo ohms, which means total resistance is 1 kilo ohm plus 3 kilo ohms because the two resistors are in series. So V out, I'm using the potential divider formula. V out is going to be R out over R total, then times the voltage supply or V in. So R out, we are measuring R out across. Calculate the V out when the value of R is 3. So R out is 3. Total resistance is going to be 4. This is 3 kilo ohms. This is 4 kilo ohms. R total is 3 plus 1, which is 4 kilo ohms. Then I'm going to multiply this by the V in, which is 6.0 volts. So that is 3 over 4 times 6. I think that is automatically 1.5 volts. Then the value of R is adjusted until the current in the circuit is 1.7 milliamperes. The current is 1.7 milliamperes. Calculate the charge that flows through the circuit in 300 seconds. So time is 300 seconds. So we know that charge is equal to I times T. So I is 1.7. It is milli, so I'll say times 10 to the power of minus 3. Then times time is 300 seconds. So because I removed the milli, the answer will be in columns. So I have 1.7 exponent minus 3 times 300 seconds. So that is 0.51 columns. So this is 0.51 columns. Next is, I think, magnetic effects. The figure shows a wire carrying a large current. Okay, so the current is down into the page. The figure shows the square card viewed from above. So from above, if the current is into the page, we put a cross. So that's why we have this cross here. On the figure, draw 3 magnetic field lines that indicate the direction of the magnetic field and how its strength varies with the distance from the wire. Number 1, your teacher must have told you that the magnetic field due to a current carrying wire are concentric circles around the wire, and they move further apart as you move away from the wire. Then you use the right hand grip rule to tell the direction. So 1, they are concentric circles around the wire which separate, which get further apart as I move away from the wire. So you put a protractor at the center here. You draw the first concentric circle using a protractor, not a protractor, a compass. The first concentric circle using a compass. Then I'll add another one. Remember, the separation increases. So if you use a compass, it is easy to notice that the separation has increased. Then you draw, they said the 3, so I'll draw the third one. The separation must increase as you move further away from the center of the wire. So you see that I have not used the compass, but the separation of my lines has increased. So they are concentric circles. They are further apart as you move away from the wire. Then using the right hand grip rule, grip a pencil or a pen in your right hand and turn it so that the thumb, which is pointing at the tip of the pen, is pointing onto your question paper, which is on the table. And when you do that, you notice that all the fingers, the other fingers, fold in that direction, which is clockwise. So it means the magnetic field pattern is clockwise. Concentric circles with the magnetic field pattern, which is clockwise. That is using the right hand grip rule. Okay. Then the current in the wire increases and the direction of the current is reversed. The direction of the current is reversed. If we reverse the direction of the current, we also reverse the direction of the magnetic field. But the current is increased, which means the magnetic field increases. So the field lines get closer because the current is directly proportional to the field strength. A greater current means a greater field strength. And how do we show a greater field strength? Is by putting the field lines closer to each other. State how these changes affect the magnetic field. Number 1, the strength of the field increases. Strength of the magnetic field increases. And of course, the direction, because the current reversed, its direction is reversed. And its direction is reversed. So the direction is also reversed. Electricity is transmitted at a high voltage. Of course, at high voltage, we know that the power dissipated in the wire is I squared R. If we transmit the same power at a high voltage, then the current which flows is very small. That means the power which is lost is also very small. Okay. Explain why a high voltage increases the efficiency of transmission even with thinner wires. So we know that power loss in the wires, power loss is equal to I squared times R. That's number 1. So for the same power transmission, for the same power transmission, for the same power transmission at high voltages, or at high voltage, lower current flows. Lower current flows, so less power, there's less power loss. There's less power loss. So at high voltage, lower current flows, so there is less power loss. But also thinner wires have a smaller cross-section area, so higher resistance, but this is less because remember, if there's less current flow, remember the current is squared, and if it is less and squared, it means the power is going to be even less. So I'll say thinner wires have smaller cross-sectional area from R is equal to rho L over area. So thinner wires have a smaller cross-sectional area, so they have a higher resistance. So higher resistance. But this is less important, or it's less significant. This is less important as there is less current. So this is less important as there is less current or there is less power loss. So the smaller cross-sectional area, which gives a slightly higher resistance, is going to be less significant as there is already less power loss. Okay, I think next is going to be nuclear physics. I don't know whether it is, no, space physics is the last, I think. An experiment that directs alpha particles at a very thin sheet of gold. Most of the alpha particles pass through the thin foil in a straight line. Of course, this implies that most of the atom is empty space. So this is because most of the atom is empty space. Most of the atom is empty space. Number two, some of the alpha particles are deflected through angles less than 90 degrees, and a few are deflected through 180 degrees. Some are deflected through angles less than 90, and a few are deflected through angles greater than 90 or 180 degrees. State and explain two conclusions about the nuclei of atoms from this observation. So, if a few are deflected through angles less than 90 degrees, is because the nucleus is very small. And number two, deflected through angles 180 degrees because the nucleus is positive. Or it means the nucleus is positive. That's why we have this deflection. The few particles deflected means the nucleus, many of them do not come close to the nucleus, so they are very few, it is very small. So number one, we can say the nucleus is very small. Nucleus is very small compared to the atom. That's why very few are deflected. So we can say the reason is because not many alpha particles get close or pass close to the nucleus. Or we can say only a few alpha particles pass close to the nucleus. Not many alpha particles pass close to the nucleus. Then conclusion number two, the nucleus is positively charged. Because we know the alpha particle is positive, the deflection is due to a repulsion. So the nucleus is positively charged. The nucleus is positively charged, so we can say the reason is because alpha particles are positively charged. Alpha particles are positively charged. and so the force between alpha particles between the alpha particle and the nucleus is repulsive. So the nucleus is positive. So we can say the nucleus is positive too. A source contains a radioactive isotope of strontium. This isotope decays by emission of beta particles. The half-life of this isotope is 29 years. State the change in the nucleus which occurs when a beta particle is emitted. So when a beta particle is emitted, of course, what really happens is that a neutron changes to a proton. That's when we have a beta particle. Because if I try to balance this, a neutron is 1, 0, a proton is 1, 1, plus when I say beta particle for IGCSE, it is beta minus, which is 0, 0, negative 1. Of course, this is accompanied by another particle which you will encounter in AS or in year 12. So state the change in the nucleus which occurs when a beta particle is emitted. So a neutron is lost, or a neutron is replaced by a proton. So a neutron is replaced by a proton. The initial mass of this isotope of strontium is the source. In the source is 25 milligrams. 25, no, not milligrams, micrograms. Calculate the mass of strontium isotope that decays in 87 years. So note that the half-life is 29 years. So let's first find the number of half-lives. The number of half-lives, my students normally call it N, is going to be 87 divided by 29, which is, I think this is 3. There are 3 half-lives. So if I start with the 25 micrograms, for the first half-life, I divide by 2. That will be 12.5 micrograms. For the second half-life, I divide by 2. That will be 6.25 micrograms. For the third half-life, I again divide by 2. That will be 3.18. Is it 3.18? 6.25 divided by 2. 3.125. 3.125 micrograms. So there are 3 half-lives. So this is a half-life. This is a half-life. This is the third half-life. So it means that after 3 half-lives, the mass remaining is that. Capture the mass of the strontium isotope that decays. So the mass decayed. This is what remains. So what decayed is going to be 25 micrograms minus 3.125 micrograms. So 25 minus the answer, that is 21.875 micrograms. Alternatively, some students decide to use the formula which is m equals to a half power n times m naught. M is mass present and m naught is the initial mass. So the mass present is going to be a half, n is half-life, then times m naught, which was 25. Of course, this gives you 1/8 times 25, which is the mass which is present. Calculate the mass of the strontium isotope that decays in that. So the mass which is present is going to be 3.125 micrograms. This is mass present, initial mass present. Then again, you have to subtract. So the mass which is decayed you'll again go back to that expression there. But that equation is normally used by year 13 students, but you can still use it if you know how to use it. Okay, this is a blank page. Question 10 is, I think this is space physics. So the figure represents different positions A to H of the moon as it rotates around the Earth. Of course, when the moon is here, we have a new moon. And when it is a new moon, you see total darkness. If you are standing here on the Earth, you will see total darkness because the moon will be blocking, the moon will be completely in the way of the Earth. So what you see from this side is just a total shadow. That's a new moon. And when it is here, we have a full moon because the light will be incident fully onto the moon. So you will see the whole of this part, this side facing you. If you are standing here, you will see a full bright part of the moon. So it means this is going to be a full moon. Set a position of the moon where an observer on Earth sees there is a quarter moon. So when the moon is either here or it is here, so for the observer, for you, because you are standing here looking at the moon, you'll just see a quarter of the moon. You'll see a small section because it's half illuminated, but if you are somewhere here, you'll actually see a quarter of this. You'll see a quarter of that. So it is in position either A or E. So this is going to be A and E. There is a quarter of the moon because this side is under shadow. This side is under shadow. The other side is bright. But remember, you are only seeing, because of your position, you are only seeing a small quarter. So the whole of this side is under the shadow, but because of your position, you only see this part here. So you see a quarter of the moon. It is the same thing here. This side is, the whole of this is under shadow, so you only see this part here. Then there is a full moon. Of course, full moon is automatically going to be in position G because the whole part which is facing you is illuminated by the moon. So that is going to be a full moon. Then state the approximate time taken for the moon to orbit around the Earth. Of course, the moon takes 1 month. There's a relationship between the word moon and the month. So the moon takes 1 month. So this is going to be 1 month, or you could say about 27 days, or about 28 days, or you could say about 30 days. This is all referring to 1 month because the average could be 27.3 days for 1 month, or you could say 28 days, or approximately 30 days. That is still 1 month. Then the average distance of the Earth from the Sun is 1.5 times 10 to the power of 8 kilometers. Calculate the average orbital speed of the Earth in kilometers per hour. So we know that our speed is equal to omega times r, and omega, remember, omega is equal to 2 pi over period. So it means the speed is going to be equal to 2 pi times r divided by the period. And if we substitute, this is going to be 2 pi times the radius, which is going to be 1.5. The one they ask in kilometers per hour, so I will not change the unit. So it's 1.5 times 10 to the power of 8 divided by the period, or the time for one cycle, because we said it is 1 month. No, it is the sun about the Earth. The sun takes 1 year, so the period is 1 year. And 1 year is about 365 days. And remember, 1 day is 24 hours. So I will say this is 365 days times 24 hours to change the time to hours. So this is in kilometers, this is in hours. So I'll press my calculator. 2 pi times 1.5 exponent 8 divided by 365 times 24. So I'm getting 10 8 or 107,588.7. So it is 0.8. So I'll round off this to approximately 108,000 kilometers. So it's 108,000 kilometers per hour. Then the speed of light in a vacuum is 3 times 10 to the power of 8. Calculate the time taken for light from the sun to reach this earth. So we know that time is equal to distance divided by the speed if the speed is constant. So the speed is constant, the distance is 1.5. They want the answer, they have not given the unit. So I'll say 1.5 times 10 to the power of 8. This is in meters per second. So this is in kilometers. Divided by the speed, which is 3.0 times 10 to the power of 8. So I'll have to make the units uniform. So this will be 1.5 times 10 to the power of 8 times 10 to the power of 3 to make it in meters. Divide by 3 times 10 to the power of 8 in meters per second. So the units are now uniform. So that will be 1.5 exponent 11 divided by 3 exponent 8. So this is 500 seconds. Because I changed the distance into meters, so it is 500 seconds. And last, I think, is space physics, still, that is astronomy. Set the condition for required for a protostar to become a stable star. Of course, we know for a protostar to become a stable star, the inward gravitational force acting on the star should balance with the outward force due to the high temperature, which is always found in the center of the star. If that does not happen, then it will not be a protostar. So the inward gravitational force of attraction must be balanced by an outward force due to the high temperature found in the center. So if the two forces are balanced, then the star is called, or the star becomes a stable star. Otherwise, it will be a protostar. Then define Hubble's constant. Of course, we know that V equals to H naught times D, which means H naught, which is Hubble's constant, is V over D. So the ratio of the recessional speed of a galaxy to the distance is the ratio of the recessional speed of the galaxy to the distance away from the observer. So this is the ratio of the recessional speed. To recede is to move away. The recessional speed of a galaxy to the distance away from the observer. So that's what we call Hubble's constant. The current estimate for the Hubble constant is 2.2 times 10 to the power of 10 times 10 to the power of minus 18 per second. State the equation which gives an estimate for the age of the universe. So the age t is equal to distance over the speed, but the distance is, so time is distance over speed, and the distance, let's say the distance is d, and the speed is h naught times d, so it means time is going to be 1 over h naught. So the time t is equal to 1 over Hubble constant. Or you can just set t equals to 1 over h naught. Then calculate an estimate for the age of the universe. So I've already said t is equal to 1 over 2.2 times 10 to the power of minus 18. 1 divided by 2.2 exponent minus 18. So this is 4.54 or 4.55 times 10 to the power of 17. 4.55 times 10 to the power of 17. Yeah, so that is 4.55 times 10 to the power of 17. Okay, so that is the estimated age of the universe in seconds. I think that marks the end of paper 4. See you in other papers of IGCSE. Bye bye.